Hi everybody. If you wanted a review of what we did on Monday, we talked about stretch nets. Here's the idea of a stretch net. Let's take a problem that's a straightforward kind of skills problem. This is an example of one that you might have had in Algebra 2 trig. So the question is solve for x. So here a lot of students would say x was equal to 2 or x is equal to 3. The idea of the stretch net is we're going to come up with small variations, small changes that we could make to this problem that would turn it into a different problem. So here are three that I would typically give to Algebra 2 trig students. So here I still have two terms being multiplied, but I've reversed the order of the constant and the x's. Here I've replaced one of them with some totally other kind of function. And here I have the two terms being multiplied, but they're equal to 1. And then you want to ask yourself, which of these problems can be solved using a similar or the same solution approach as the original, and which problems need a completely different approach to them? So usually you go through really quickly and just make an estimate. Or not an estimate, but you make a quick guess. So you could say, all right, this one I know for a fact it can be approached the same. This one I can't tell. And this one I know definitely can't. So you would do that. It's okay if you end up marking most of them as question marks, because sometimes you really can't tell for a lot of questions. Then when you practice, a great thing to do would be, if you know it's the same solution technique, but you feel like it would be good for you to practice, go ahead and solve those problems. If you don't feel like you need extra practice at that basic skill, then don't. Then start looking at the question mark problems and actually try and see, does the same idea actually work out, or do you need a different approach? These are sort of the extending your thinking questions. You could also extend your thinking by trying to tackle ones that you know are definitely different by coming up with new solution approaches. The thing about coming up with your own problems is you don't really know if they're really, really hard or really, really easy. And that's actually a good thing. That's more authentic to what doing math in the real world is really like. Because the problems come from the world itself. They don't come from some teacher that's trying to give you problems at exactly the right level for exactly what you've been doing. So for this kind of problem, a lot of Algebra 2 trig students just pattern match. They say, when I see a problem that looks like this, I know that I do that. The underlying concept, which you probably learned, was the zero product property. So the idea is this whole thing is just a number. That whole thing is just a number. And if you have two numbers multiplied that equal 0, it has to be the case that either the first number is 0 or the second number is 0 or both. So that underlying idea applies here just fine. We could rewrite this as 3 minus x is 0 or 2 minus x is 0. And now that gives you two solutions. This, even though it looks quite different, is still the same pattern because e to the x is some number when you plug in a value for x. So I've still got two things being multiplied equaling 0. So now I know either e to the x is 0 or x minus 2 is 0. This leads to the solution x is 2. E to the x equals 0 you might have to think about for a minute. You could think about it either numerically or graphically. I tend to like to think about things graphically. So I know that that's the graph of e to the x, and I know that there is no x value I could plug in that would make the e to the x evaluate to be 0. So I know that this path doesn't actually lead to solutions. But my point for you is that even though the problem appeared quite different on the surface, the same underlying idea applies. And that's the kind of thinking that you want to be using when you practice, in your independent practice and also in the classwork assignments, is don't try and pattern match on the surface. Don't try and think of what should I do for a problem. Instead, focus on what's the important underlying concept for the problem. So here, even though this one looks more similar to the original one than that did, the underlying concept doesn't apply, because here I've got some number times another number equals 1. And there's all kinds of pairs of numbers that multiply together to be 1. So that doesn't let you break the problem into two smaller, simpler parts that would lead to solutions. So for here, probably your best bet would be to expand and then collect all the terms on one side and complete the square or use the quadratic formula. So then we practiced this idea as a class. I said, let's pretend this is our problem. Well, it's not a problem yet. It's just two equations. Let's add the problem. OK, graph the set of parametric equations as t ranges from 0 to pi. And then I had the class come up with small variations that maybe would be the same kind of problem and maybe would be different problems. So here are a couple things people came up with. What happens if you reverse the two equations? So now x is sine and y is cosine. What happens if you have sine of t plus something and cosine of t plus something? And the something here could be like pi over 2 or 10 or kind of whatever you wanted it to be. Some people thought, what if instead of dilating by 2 and 3, you actually dilate by time? What if you dilate by t? What if you applied some function to each of these parts? So what if we squared each of them? Or what if we took the square root of each of them? What if instead we had an inner function on t? So we replaced t with 1 over t, or t squared, or root t. You don't just have to do small variations on the equations. You could change the problem. So what if the problem is not to graph this, but to come up with two new equations that trace out the same graph, but trace out the graph backwards, for example, or trace out the graph more quickly? Another group said, what happens if you change the domain for t here? So there's a lot of interesting possibilities. And your homework due next Monday is to complete your own StretchNet with a bunch of examples of this, and then choose one problem that you think is essentially the same as the original. Same concepts apply, same solution approach, sort of nothing different, it's just like the numbers changed. Or, oh, sorry, not or, and choose one that you think is substantively different and then discuss kind of what is it about the problem that makes it different. And I'm not just looking for surface level, like, oh, adding something on the inside made the problem different. Because sometimes you make a change to the equations and the problem isn't substantively different. So I'm not looking for a surface level what's different. I'm looking for adding something to t on the inside makes the problem different because, and then you explain kind of why that particular change ended up mattering, whereas other types of change wouldn't have ended up mattering. That's it.